Today we'll be talking about the Fundamental Theorem of Calculus, the very more general one compared to the one you learned in Calculus 1. This one is going to be the one that you most likely would learn in Calculus 3. So just a quick review. In Calculus 1, you have some function of x, dx. You have your bounds a, b. And you're going to have some antiderivative, some function, capital F. So capital F is the antiderivative of the function, or the integrand of this integral. And you can plug in for b, you can plug in for a into this antiderivative and subtract them from each other in order to get the answer for an integral. But for line integrals, you can do it like so. So let's say you have a line integral, you have some vector field, and you dot it with your tangent vector, represented by r prime. Again, even though your functions are not scalar functions, it will become a scalar function once you parameterize using dot product, and then use dot product. But you can also solve this using an easier method. So you have a potential function. This is called the potential function of psi. You might see it as little f as well, as the vector field is represented by capital F. But I'm going to be using psi for the Greek alphabet here. And this potential function has specific conditions in which you can actually apply this theorem. These specific conditions are simply connected. So what does simply connected mean? Simply connected. Well, in order to apply this, you need some closed boundary. In order to apply this theorem, you need some closed boundary. And this circle on the line integral stands for a closed boundary. So let's say you had a graph, and you had, I don't know, a semicircle that wasn't closed. In this case, it's open at the bottom. Well, you can't apply this theorem. But if, let's say, if you had a full circle, and it was an actual full circle, the entire thing was, not covered. Let's try to make this actual circle. There's no holes in this, then it's simply connected. But let's say you had some undefined region here, represented in, let's choose purple. Represented in purple, undefined region, and you try to find your potential function along this closed region, but there was a hole, then it is not simply connected. But if your domain is defined on the entire R2, and you had some hole here, but your closed region was somewhere outside of this hole, then you could still apply your theorem. So simply connected just means there's no holes within your boundary. Your vector field also has to be conservative. Which means that the curl, or the del operator, cross product with your vector field is equal to 0. And soon I'll post a video on how to make or solve for curl. But just a quick summary, your del operator is just equal to a vector, a bunch of components of partial derivatives, like so, depending on the amount of components you have in your vector field, of course. And when you have a conservative function, it also means that the gradient, so the gradient of your phi function, or potential function phi, is equal to your vector field. So let's give you an example of that. Let's say you have your phi potential function is equal to, I don't know, x squared y plus z. Then the gradient of this would be equal to, so your x partial. So your x partial would be 2xy. Your y partial will be just x squared. And your z partial will just be 1. And if this right here is your vector field, then your potential function would look like so. And there's multiple ways that you can solve for this, but usually you're going to have one answer. But a large part, or the hardest part about solving for these problems, is just finding your potential function given your vector field. I'm going to have a video on how to solve for that. That's the next one I'm going to be posting. And just a quick side note, Fundamental Theorem of Calculus isn't only comprised of, well, your line integral form. It can also have something called the Green's theorem, Stokes' theorem, and divergence theorem. But those aren't until later.